Halloween, and that's over for another year.
Alrighty, good morning everybody. Welcome back to non-Euclidean geometry. Plan for today, we're going to finish off this packet. Hopefully. If not, we'll finish it early in class on Wednesday. Mainly focusing today on triangle inequality, after we talk a little bit more about this theorem, which we sort of covered last class. I've got my usual office hours, today and Wednesday, after class, and from 2 to 3, tomorrow at 11, and at 1 o'clock. And as far as homework goes, don't forget you have your take-home exam due tomorrow. Dr. Gerstle, what time tomorrow? Glad you asked. Anytime tomorrow. By 11:59 p.m. tomorrow, you can either, just if I'm not around when you want to turn it in, just put it in the mailbox outside my door. Technically, yes, that does mean you probably have until something like 8:05 a.m. Wednesday morning, or whenever I actually get into the office. Any questions or comments before we get started for today? So, Rene Descartes walks into a bar. He goes up, orders a drink, bartender gives him a drink, nurses it down, bartender asks him, would you like an A? You want another? Descartes thinks about it for a minute and says, So again. The bartender is very polite. Bartender says, would you like another? Descartes thinks about it and says, I think not. And then immediately vanishes. Because now he is.
Where's the math?
It's Descartes! You know, guy basically created analytic geometry.
Ugh.
What kind of question is that?
How many fights can I start today?
Don't test me. So last time we talked about a version of a theorem that allowed us to kind of uniquely assign angle values to angles in any Hilbert plane that had at least Archimedes axiom. And it basically said a bunch of nice things about, how angles are right if and only if their measurement assigned to them is 90 degrees. Supplementary angles have to add up to 180 degrees, yada, yada, yada. And at the very end of class, we started talking about a very similar theorem for assigning the lengths to line segments. And the idea is, if you're given some fixed segment that's defined to have length 1, and there's my segment, I'm going to call whatever the length of this is, I'm going to call 1. Then there's a unique way to assign a numerical value, which we'll call length, to every other line segment in our model in a way that has a bunch of nice properties. Like the length of a line segment is always some positive real number. Two line segments are congruent if and only if the number we assign to their length is the same. Oh, and by the way, putting a bar above AB just means the length of AB. Given 3 collinear points, B is between A and C, if and only if the length of AB plus the length of BC is equal to the length of AC. So if we have an A, a B, and a C, we're basically saying the length of this plus the length of that equals the length of the whole segment from A to C. The length of AB is less than the length of CD if and only if AB is less than CD. What does it mean to say, by the way, that one line segment AB is less than another line segment CD? What?
If you do Archimedes axiom, Archimedes axiom, where it would be that AB, if laid on once, B would be between C and D.
Yeah, that would be one way to think about it. If we want a way that doesn't rely on looking at Archimedes axiom at all.
You can take the ray AB and there is a point on the ray AB such that B is between A and we'll make a new point E, that's congruent to CD.
Yeah, exactly. So that we could make AB congruent to CD. Or equivalently, we could say something like, there exists a point E between C and D such that AB is congruent to CD that way as well. So basically, we have some sort of betweenness and congruent idea going on that basically says this definition of AB less than CD is equivalent to being able to say that the length of AB is less than the length of CD. And then finally, the fifth kind of unique thing that we get is that for every x greater than 0, there exists a line segment AB whose length is x. So Lacey, if you were to try and give me some horribly nasty positive real number, like say square root of pi over 17, that means there should exist some line segment out there that has that length to it. Question. For every x greater than 0, there exists a segment AB with length of AB equals x. Is that AB going to necessarily be unique? Or could we have two line segments whose both of whom have a length of x? This is not a trick question. Although I know by saying that now you're wondering if there really is. Good?
Yeah, of course.
It is unique?
Oh, no, none. Sorry.
It is not unique.
The second one, yeah.
Here's my proof. You see how this has length 1? Boom, there's another one of length 1. So when we say that there exists some segment whose length is equal to x, that doesn't mean there's only one segment that does the job. There's infinitely many typically, and I think actually in any model of any Hilbert plane you can prove that there are infinitely many. Or at least if you have Archimedes axiom, I think you could prove there are infinitely many. But there's at least one that gets the job done. And as we said last time, 1, 2, 3, and 4 you can get from Archimedes axiom. Whereas for number 5, you need the full strength of Dedekind's axiom. Or Dedekind's axiom. Archimedes' axiom is the one relating to laying off a line segment on itself multiple times on an array. Whereas Dedekind's axiom is the one that says if you take any line and you break it up into two sets, no point of one is between any 2 points of the other, then one of your sets has to be arrayed. And here is something that's spicy. The guy asked a question in the packet of, what do we know about Hilbert planes satisfying these properties on line segments? Turns out that if you have these 5 properties and you're working over a Hilbert plane, and let's say if these 5 properties uniquely hold over a Hilbert plane, refresh my memory, what's a Hilbert plane? Okay.
Plane that satisfies the IVC axioms.
Yeah, it's the model of the incidence between his congruence axioms. Turns out that if you have the incidence between his congruence axioms and this theorem turns out to be true, that there's a unique way of defining line segment length given your measuring stick of length 1 that you started with, then Dedekind's axiom must also be true. So in other words, in a Hilbert plane, this theorem is logically equivalent to Dedekind's axiom, in that you can use this result to prove Dedekind's axiom, and you can use Dedekind's axiom also to prove this result. That either one being true automatically implies that the other one must also be true, and conversely false. If one is false, the other is false. And as long as you're working over a Hilbert point. Any questions or comments? All right, I tricked you. We're done with this packet. We're not actually done with this packet, but the rest of this packet and the next packet are all going to be about a common subject, which is triangles. So specifically, between this packet and the next packet, we're going to be looking at properties of triangles that have to be true in a Hilbert plane, and properties of triangles that may or may not have to be true in some Hilbert plane that we could be considered to be working over. So first thing I want to do is everybody's favorite, the triangle in, yes, Megan, equality. Well, we're going to prove that, my goodness. We're going to prove that given any triangle in a Hilbert plane, so in any model of neutral geometry that we're looking at, it's going to be the case that if you take the sum of any two side lengths, you're always going to get something that's greater than the third side length. Let's do it in yellow, why not? So here is our theorem. So if AB, BC, and AC are the lengths of the sides of a triangle, then the length of AC has to be less than the length of AB plus the length of BC. So in other words, if I draw out a triangle down here, let's say this is A, this is B, this is C, then, and assume we've defined length in a way that works with the previous theorem, that satisfies all the properties in the previous theorem, then the length of the side from A to C has to be strictly greater than the length of the side going from A to B plus, or sorry, has to be strictly less than the length of the side from A to B plus the length of the side from B to C. Which kind of intuitively, this basically says that the shortest distance between 2 points is the straight line segment between them. You can't take another path like that goes by 2 segments and get there any faster. So here's our proof. So to start with, I claim there exists a unique point D on the ray AB such that B is between A and B, I should say, and BD is congruent to BC. So in other words, I claim we should be able to find a point approximately there, such that the length of this side of the triangle, BC, is equal to the length of that side of the that segment from B to D. Why do we know that? Why does there have to be a point D that does this? Jared?
I think that's Congruence Axiom 1.
That is indeed as a result of Congruence Axiom 1. Or if you remember, Congruence Axiom 1 is the one that says that given any given any line segment in any ray, you can always cut that ray off at a point to produce a line segment that was congruent to the original one. So here, we're basically taking the ray from A passing through B. And according to this, there should be some unique point on the ray, on this ray going to the right of B, such that BC, this fixed line segment here, is congruent to this other new one that we create, BD. And since these are congruent, BD is congruent to BC, that's going to tell us that BD and BC have the same length, according to the theorem we just proved. And what I'm actually going to do is we're now going to connect CD by a line segment. And we're actually going to say something a little bit fancy here. And no, we're not going to say that. So first of all, we can say that since B is between A and B, what does that tell us about the length of AB plus the length of BD? In other words, if we take the length of the segment going from A to B and add that to the length of the segment going from B to D, right? Right, equals the length of the segment from A to D. That was part 3 of the proposition from Hartshorne that we just looked at. You know, that AB plus BD equals the length of the segment from A to D. Thus, the length of the segment from A to D, I claim, is going to be equal to the length of the segment from A to B plus the length of the segment from B to C. The reason being, the length of the segment from B to D, we know, is going to be equal to the length of the segment from B to C, because BD and BC are congruent line segments. And by property 2 of the proposition part 2 of the proposition we just looked at, if two line segments are congruent, then that means their lengths have to be equal to each other. So now we know that if we take this big line segment from A all the way out to D, that's going to be the same length. That's going to be what we would get if we took the length of the segment from A to B and added it to the length of the segment from B to C. So our ultimate goal is this expression right here. We'd like to show has to be strictly greater than the length of the segment from A to C. So our goal for the rest of our proof is going to be to show that that the length of AC has to be less than the length of AD. Because if we can show that the length of AC is strictly less than the length of AD, then that will prove that the length of AC has to be less than length of AD plus length of BC, which is what we're trying to show. Any questions or comments so far? Okay, here's where we're going to have to use a couple propositions we haven't really talked about, but that I think you've all probably seen before in high school geometry and are probably unsurprised to see here. We could say that since the ray CB is between the ray CA and CD, angle ACD is going to be greater than angle BCD. So in other words, since this ray going from C to B is in between the segments going from C to A and the segment from C to D, what that's going to tell us is that this angle, ACD, is strictly bigger than the angle BCD, and this one right here. So this angle kind of is part of this larger angle of the big triangle I've made, so this angle should be smaller than that one. And then we can say that Also, I'm going to note that since BC is equal to BD in terms of length by construction, how we originally constructed it, we know that the angles opposite sides BC and BD have to be equal. So angle BCD is going to be congruent to angle CDB. In other words, I'll erase this. This white angle here has to be equal to that white angle. And here, this is using a proposition we never really talked about, but it's a proposition that basically says if you have an isosceles triangle where this side and this side have the same length, then it's going to turn out to have to be the case that the angles opposite those two sides have to be congruent. So if these two sides are the same length, then these two angles have to be congruent. And we haven't talked about that yet, but that is something that is going to be true in a Hilbert plane and can be proven as a result of using our proposition about angles and assigning measurements to them. So we know that angle ACD is greater than angle BCD, and angle BCD is congruent to angle CDB. So that's going to tell us that angle ACD is greater than angle CDB. Go back to my yellow chalk. Angle ACD has to be strictly greater than angle CDB. This top angle of the big triangle has to be strictly greater than this angle down here. And now I'm going to use another result which says that if we have a triangle that if you have two sides of a triangle where one side is bigger than the other side, then the angle opposite that bigger side has to be bigger. Sorry, I'm doing this backwards. If we have two angles in a triangle where one angle, say this angle, is bigger than this angle over here, then the side opposite the bigger angle has to be bigger than the side opposite the smaller angle. So if we have two angles in a triangle that are different, then the bigger angle is going to be opposite the bigger side of that triangle. And we'll apply that here. To say that since angle ACD is greater than angle CDB, which side is opposite ACD? In this triangle. So if we look at this bigger triangle with angle ACD being the upper angle in this big triangle, what side in the big triangle is going to be opposite from this angle? That?
Side AD.
Yeah, so that's going to tell us that side AD has to be bigger than the side that's opposite angle CDB. So if we take angle CDB in this triangle, where here the triangle is the big triangle, what side in our big triangle is going to be opposite angle CDB? Or dare I say angle CDA? Okay? Yeah, side AC. So since bigger angle has to be opposite to the bigger side, that's going to tell us that the length of AD is strictly greater than the length of AC. And now we're basically done, because that was our goal, was to show AD is greater than AC. Oops. points down here. Thus that, and then since that's greater than that, AD is greater than AC. And then we can say, well, since we knew that the side of length of AD is equal to the length of AB plus the length of BC, we can conclude that the length of AB plus the length of BC is strictly greater than the length of AC. And we are done. Any questions or comments about this? I've got a question. So we've shown that in this triangle, ACB, that the length of AC has to be less than the length of AD plus the length of BC. Do we know that AB has to have a length less than the sum of the lengths of the other two sides? In other words, do we know that AB has to have smaller length than length of AC plus length of CB? Elaine?
Yes, because it's arbitrary where you assign the points based on the theorem. Like it's not saying, because you could just move like C and B, and then you could use the exact same lettering that's up there.
Yeah, so in other words, it basically just comes down to, you can relabel all your points, and then the exact same theorem would also show that AB has length smaller than the length of AC plus CB, and similarly, BC has length smaller than CA plus AB. But just by relabeling your points, you could show that any side in this triangle has to be less than the sum of the lengths of the other two sides. Luke?
I guess you just said it. So is there a corollary to this that all sides of any triangle, any one side of any triangle must be less than the other two sides of the triangle?
Yeah. I don't know. I didn't even write this down as a corollary, because it's literally just a matter of relabeling your sides. How you just label the sides. But yeah. From this, you could say that, you could exactly say that. That's true. I'll just write this in here as a comment. From this, it follows any side of a triangle has length less than the sum of the lengths of the other two sides. Any other questions or comments about how we prove the triangle inequality? Yeah, so we did rely on these two results which we never proved, which is if you have two sides of the same length in the triangle, then the angles opposite must be equal. And similarly, if we have two angles where one's bigger than the other, then the side opposite the bigger angle has to be longer than the side opposite the smaller angle. But these are things that can be proven, and yes, I am considering giving you one or both of these in the next 20%. So this is actually our textbook, Greenberg. Don't ask me why the packet says Steinberg, that's a typo. That's a typo that involves me confusing my math textbook authors.
I like that.
So it turns out, how is Euclid's proof compared to this one? Euclid's proof is actually basically the same. It's just sloppier. You know, as Euclid is wont to do.
He's doing his best.
He's doing his best, I know. Gosh, when I taught Math 105 last year for the first time, I tried to point out throughout, like, because we look a lot at Euclid's elements and I'm like, oh, this is something that Euclid could have done better, but But give him a break. He's like the first person ever trying to systematically, axiomatically prove all of these things. At the end of the semester, I got a comment from one of my students, my eval, saying something like, "This feels like he was just talking about how Euclid is an idiot the whole time." And I didn't like that. I'm like, "Oh, no, that's not what I wanted to say."
Is that how you grade R proofs? You're like, that's exactly what I had, except just worse.
Pretty much. It's like, this proof looks
I know
like
that's what Gabler does.
this proof looks like it could have been written by Euclid. 1 out of 4.
This is the best thing you have.
This is worse than.
Somehow you managed to actually be worse than Euclid. No, I don't want this. No, I didn't want that class. I don't want this class to just be entirely about shitting on Euclid. Because Euclid is rightly famous for kind of putting together the elements, and if you were to try and basically be the first person to create this careful axiomatic way of looking at math, you try doing it perfectly and unambiguously and using very precise definitions yourself for the first time. It's easy for us in retrospect, like thousands of years later, to look back and say, that's silly Euclid. He thought you could move around line segments and it doesn't change anything, even though he didn't state it as an axiom. Or, silly Euclid. He thought these two circles had to intersect. I know, hilarious, right? But in actuality, what he did was like a monumental accomplishment in creating the elements, and I just think it's good. I think it's just good as a learning exercise to kind of say, in retrospect, what are some things you could have improved upon. That does not mean Euclid is an idiot and you shouldn't do anything like that. Anyways, Euclid's proof of the triangle inequality. This was in book 1. Is similar, but a little more slow. So Euclid, for instance, didn't have any way of saying things like, oh, the length of AB plus the length of BD has to be equal to the length of AD. That's something Euclid just kind of assumed as sort of like, oh, that's a common sense thing to assume. But maybe from nowadays we might look at something like that and say, hey, sure. He didn't have any formal reason to say why something like AB plus BD. Euclid's proof of that would be, Euclid's argument for something like that would be, well, I mean, just look at the picture, it's obvious. And then suddenly his proof is not independent from the picture. Where something we're trying to do with all of our proofs in this class is to be able to relate everything back to propositions and or axioms, like Congruence Axiom 1. This picture is just something I drew over to the side as a formality, as sort of, or a visual aid to help understand what's going on in the proof, but our proof should not rely in any way on the picture. Whereas Euclid's proof of the triangle inequality definitely relied on, clearly these have to add up to that. Let's take a look at the converse of the triangle inequality. So triangle inequality says if you have a triangle, then the sum of any two side lengths has to be less than the lengths of the other two sides. So this theorem is going to be the converse to that. So, given an implication A implies B, the converse to that implication is going to be basically B implies A. So basically reverse the if and then parts of your statement. The triangle inequality says if we have a triangle and these are the lengths of the three sides, then here's an inequality involving the lengths of the three sides. If we flip that on its head, and say, suppose we have two numbers, or three numbers, where one number is less than the sum of the other two numbers. Does there necessarily exist a triangle whose sides are those three lengths. So what this says is, suppose A, B, and C are positive real numbers, such that the sum of any two of these is greater than the third, meaning A plus B is greater than C, A plus C is greater than B, B plus C is greater than A. And according to this theorem, then there must exist a triangle whose side lengths are A, B, and C. So for instance, if Elaine were to try and say, Dr. Gerstle, I'm thinking of three numbers, A, B, and C, where A plus B is greater than C, A plus C is greater than B, B plus C is greater than A. Say, I don't know, let's say Elaine wasn't being particularly original, and gave me A equals 5, B equals 12, C equals 13. Five plus 12 is greater than 13. 5 plus 13 is greater than 12. 12 plus 13 is greater than 5. I claim I can, if this theorem is true, the converse of the triangle inequality, then I should be able to construct a triangle whose side lengths are this. And what can we say about a triangle in at least Euclidean geometry whose side lengths are lengths 5, 12, and 13? What kind of triangle is that going to look like, Megan? It's a right triangle from Euclid's converse to the Pythagorean theorem. Because 5 squared plus 12 squared equals 13 squared. Boom. I constructed a triangle whose side lengths are 5, 12, and 13. In Euclidean geometry, this would have to be a...
She was like, how did you know? I thought she did the squares in her head.
I mean, 5, 12, 13. I mean, 5, 12, 13 is like the second most common Pythagorean triple after 3, 4, 5.
Never heard of it. No. I know 1, 1 and the square root of 2.
Well, we're going to have a fun conversation about the Pythagorean theorem next topic.
Okay.
Let's see. I'll let anyone answer this one. If I were to give you, say, an A equals 8, a B equals 17, and a C equals 7, can we construct a triangle whose with those side lengths? Yeah?
No,
Why not?
because 8 plus 7 is 15, and that's not greater than 17.
And so, okay, does that follow from this theorem that we can't, from the converse to the triangle inequality, that we can't construct a triangle like that?
No, but it follows from, if you make a triangle with those three lengths, then you would break the original triangle inequality.
Yeah. Technically, this doesn't say we couldn't construct a triangle whose side lengths are this. It doesn't say we can, but it also doesn't say we couldn't. But the original triangle inequality would tell us we can't construct a triangle with these side lengths because if such a triangle existed, it would break this theorem, not that theorem. So I'm going to say a triangle with these side lengths can't exist by the original triangle equality. So question. Are these logically equivalent statements? Here?
It doesn't seem like it.
Well, let's ask a more general question. It's not relating to these two specific statements. If I were to give you an implication of the form A implies B, is that going to necessarily be equivalent, logically, to B implies A? Elaine?
No.
No? Can you give me a counterexample?
Yes. Okay, so like Cauchy sequences are always convergent, but
Can you use a counterexample that doesn't involve stuff we haven't learned in this class?
No. That
I
was
did.
all I had.
A square is over a rectangle, but a rectangle is over a square.
Ah, so
Maybe
state
more than this class either. Yeah.
quadrilaterals are 2 packets from now. I say the one I had in mind is if x is a multiple of 4, then x has to be a multiple of 2. But if x is a multiple of 2, x doesn't necessarily have to be a multiple of 4. So the answer ends up being not necessarily. What is A implies B logically equivalent to that's similar looking to this? Jack?
That not B implies not A.
Yeah, which is called the blank of the original implication.
Contrapositive.
Indeed. Yeah. A implies B is going to be equivalent, logically, to not B implies not A, but not to B implies A. In other words, in general, a mathematical statement is going to be logically equivalent to its contrapositive, but not necessarily to its converse. I say not necessarily because obviously we have statements like, if x equals 2, then x equals 2. Okay, if we flip that one around, then yeah, clearly it's still true. But the converse doesn't necessarily have to follow from, or like if x equals 2, then x plus 1 equals 3. That's a better example. Obviously, yes, if x plus 1 equals 3, then x still has to equal 2. In the real numbers, the way we're used to thinking about addition. But you could have statements like some of the ones we threw about just now where the converse, where the original statement's true, but the converse is false, or vice versa. The point I want to get at here, these are not logically equivalent. So, turns out that triangle inequality is true in any Hilbert plane. At least any Hilbert plane with Archimedes axiom. But the converse needs one extra axiom in order to be true. So here's my question. What do you think the converse needs to be true? I'll give you a hint. It's one of our continuity axioms, and it's one that Euclid maybe struggled with a little bit. That's something Euclid maybe assumed implicitly, but never wrote it down as an axiom of any sort. That?
Circle, circle continuity.
It's circle, circle continuity. So it turns out that if you have a Hilbert plane where Archimedes axiom is true, but circle-circle continuity does not hold, then the original triangle inequality has to hold, but not necessarily its converse. But if you're working in something that has both Archimedes axiom and circle-circle continuity, like let's say you're working over a model that has Dedekind's axiom, which implies both of these things, then both the triangle inequality and its converse will turn out to be true. Dr. Gerstle, I have a question. Can you give me an example of a Hilbert plane that has Archimedes axiom but not circle-circle continuity? That is a good question. And by good question, I mean bad question, because such things are terrifying to look at. Trying to define a model of geometry where you have Archimedes axiom but not circle-circle continuity. You can't use R2 because R2 has both. We're not going to see any in this class, but there are models out there where we have Archimedes axiom but not circle-circle continuity or Dedekind's axiom. Just know that such things behave very, very weirdly. And if I tried to define one carefully, it would take like a week of class time to do, so I don't want to. Any questions or comments? All right. All right, true or false? If we're working in a Hilbert plane, angles in a triangle add up to 180 degrees. Jared,
My guess is true.
your guess is true.
Yeah.
Interesting. Your guess would be incorrect.
Okay.
Turns out they don't have to add up to 180 degrees, necessarily. If we're working in a Hilbert plane that satisfies Euclid's parallel postulate, then they're going to add up to exactly 180 degrees. But it turns out that if you have, say, a different sort of parallel postulate going on, you could say something else about the angle sums in the triangle. I could say, what about if we're in a sphere when we've seen examples of triangles with like 3 right angles? Well, that's not a Hilbert plane, so that doesn't actually disprove this. Turns out there are other counterexamples of Hilbert planes that don't have Euclidean parallel property, where the angles don't add up to 180 degrees. And we'll take a look at some of those in the next topic. I think that's a good stopping point for today. When we come back on Wednesday, we will continue our discussion of triangles and kind of see, we have the triangle inequality still works in an arbitrary Hilbert plane, which is nice. That's a nice property to have. But it turns out some of the other properties that we know about triangles in Euclidean geometry may not turn out so nice. Hope you all have a good rest of your day. Don't forget your exam's due sometime tomorrow. You know what? Let's just put this. Exam is due class time tomorrow. Or Wednesday. Class time Wednesday. Just so if you want like Wednesday, a little bit Wednesday morning to work on it, you can. And you can just turn it in class if you like. Otherwise, I will see you all on Thursday.